Yep.
There's really not much to it, to be honest. I mean, when you first, if I were just to say we're going to now start doing equations with trig functions in them, some of you guys might, oh shit, but it's, if you know your angles and the outputs and the rest of it's not that difficult really. So 7.4 and 7.5 should be kind of a lot nicer than the earlier ones. Right? Should be.
Now we're doing 8.1.
Now we're getting 8.1.
You'll be happy to see them.
So I think every now and again before today I was kind of making references to this possibility. There's more ways than just x, y to find a point on a plane. And I think at one point I remember standing about right here and saying you could have somebody turn a certain angle and then go out a certain distance. And that's more like what ships do on the ocean. You talk about your bearing, and then you go so many miles in that, at this bearing, and that's related to the I don't really pilot a boat. So it's related to whatever the hell 0 degrees points to. You turn away from that, and you go out a certain distance, and that's where the island is, or that's where the people to rescue, or whatever. So you're heading. Yes. We've got x, y, but the other possibility is sort of like the unit circle kind of expanded. So if I want to find this point, that would be the point x1, y1. That's exciting. Or it could be the point I turn by this much and I go this far. So it would be the point r theta. It's called polar coordinates. Technically, I always felt they should have put the theta first, but I wasn't around when they were doing it, so too bad for us. It's r theta. Because it makes more sense to have somebody turn some way and then walk instead of walk out and then figure out, well, if I want to turn, I have to walk down. Screw it. Turn and then walk, but oh well, too bad. How are we doing so far?
What's that? What does that say?
Cartesian?
Cartesian.
Cartesian.
That's another name for. Yeah, it's from Descartes. Cartesian. That looks the same as before. What's another name for the Cartesian coordinate system, our normal x, y? And currently enough, it's also known as the rectangular coordinate system.
Is there R in there?
Yeah, CAR.
Yeah. So it's Cartesian. All right. So any point, if I want to find this point, I can do x and y, or I can do turn by this angle and then go out this far. So they both are valid ways of locating a point on a plane. So xy just happens to be the most often used one. It's the one we learned first. It's the one we're most comfortable with then. It's too bad in a way that we don't learn r and theta as a possibility earlier. They're both completely valid ways to do this. The problem with learning r and theta is we don't really know how to operate with theta until you learn some trig. So that's why we have to wait until later. So what we want to do, or what I'm going to make you want to do, is to figure out how to translate between the two. So if I had, for example, the point 3, 4. Somebody help me out. What would this r be? Yeah, r would have to be 5. 3, 4, 5 triangle. So in general, what would r be? R squared. What's r squared in general then? Related to x and y. How did you get 5?
X squared.
Yeah, x squared plus y. So r squared is x squared plus y squared. Cool. Now how am I going to get this angle? This is the angle that actually I have to turn through to go out 5 to get to the point that would be 3, 4 in rectangular coordinates. Beautiful, I love it, because I have to relate theta with what I would rather relate it with x and y. Because r is something I have to figure out. I want to relate it to something I know already. So theta or the appropriate reference angle. You gotta be careful, right? So to be more correct, you actually normally see this written like this in a book. For example, like our book. Because that eliminates the need to say something like, maybe it's not this, maybe it's some reference angle that uses, this is the reference angle for. You gotta be careful about that. So this is the more right way to write it. So we have this, and we have this. Do you see how that makes a way to convert from rectangular to polar? What the hell do I mean by that? If I just give you a point out of nowhere. So here it is in Cartesian. If I give you a point 7, let's not make it too freaky. 7, 2. Can you convert that into polar?
Yes.
R theta. What's r going to be? What's r squared going to be? How would I get r? R. Yeah, and again, if I drew 7, 2, r would be that hypotenuse, so it's going to be x squared plus y squared. It's always going to be x squared plus y squared. But I don't want to have to always draw it out. My God. I should be able to just convert, give me a point, I should be able to convert it into the other system. I should have to draw it every time. So the rule is r squared is x squared plus y squared. So r squared is 53, so r is
the square root of 53.
And not plus or minus. It could actually be negative, but we'll get to that point. That would be like telling somebody, turn this way and then walk backwards 4 steps. That would be a negative 4, r. That'll come up later, don't worry. How are we doing so far? Nothing major here, right? Now what would the angle be? Tangent theta must be what? Doesn't really matter, to tell you honestly, but we do want to move towards radians more often, so. Tangent theta must equal what ratio? Good. Y to x, 2 to 7. So theta would be the inverse tangent of that. Whatever the hell that is.
So we do that on our calc?
Yep, do that in your calculator. So inverse tangent of 2 divided by 7.
0.2782.
Which makes sense, doesn't it? Shouldn't that be a pretty small angle?
Uh-huh.
Okay, cool. Because it's 7, very small angle. How are we doing so far?
Good.
So somebody told me, go to the point described by, go to this point, where'd it go? Square root of 53, 0.278. That would be basically the same as going to the point 72 in rectangular. Did I turn him on?
Mm-hmm.
Okay.
Yeah, you're good.
All right, let's do another one real quick. So figure out what this point would be in polar coordinates. Now, here's where you got to be careful about which quadrant is that in. Second. Back 3 up 5. So I'm in the second quadrant. Whatever answer I get for my angle, I've got to make sure it's going to be in the second quadrant. So I got to treat it like a reference angle, whatever I get here. So r squared would be 9 plus 25.
34.
34. So r is
Square root of
root 34. Cool. Root. Yeah. Tangent theta has to be negative 5/3, right? Y over x. So what do you get for theta?
Oh, shoot. Oh, yeah. Negative 1.0.
Say again, sir?
Negative 1.030.
Negative 1.030. Okay. What's up? Now, of course, that's not theta. Possibly. Hmm? Reference angle. So it would be negative 1.030 would be down here. And I want to be up here. So what do I add on top of that? Pi. Cool. Or you think about it like, another way to think about it is pi minus 1.030 to get to it. Either way you think about it, you're going to end up doing the same thing. So theta is actually pi minus 1.030. Right? Which is 2.11. As long as I can do that in my head, maybe. I don't know. So this point would be root 34 and 2.11 rate. How are we doing? What's up? Now, just to confuse the issue, let me bring in the idea of a negative r real quick. If I did turn negative 1.030 to get to the point here, to get to negative 3.5, if I turn by this much, let me make that a little bigger because the people in the back are probably like, what the hell is he drawing? All right. So here I got my negative 3.5. So I want to be up there. If I do turn by an angle of negative 1.030, how far would I have to walk to get there? I really wanted this to line up. Do I walk forward root 34? That would end up down here. So I better walk backward. So you could do that. Personally, I try to keep things positive when I can, but that describes the same point as this. Okay, so you know trig has always got these interesting, there's always more than one way to write something, because of the fact that I can make r positive or negative, so I can walk forward or backward. So I can do an angle with an r, or I can do pi further away and then negative r. Now, both of those would get me to the same place. Maybe. It's just the idea that I can walk forward or backward. So there's going to be two different options at least. And of course, we have built into it all the freaking reference angles you can imagine for this. Will get you to the same place too. There's a bunch of different ways to write the same point. Okay, you guys look very excited. About this point. What's that? Where are we at? Oh yeah, because of this guy. Yeah. So how do I go the other way? So we have conversion from Cartesian to polar. What about going the other way? We always have to go both ways in mathematics. Right? So from polar to Cartesian we got, from Cartesian to polar we got, what about polar to Cartesian? If I give you an r theta, can you convert that to an xy? So if I give you 6 and pi over 6. Now graphing this would be a little bit more challenging. And I'm going to give you a handout in a minute that's going to show you the type of, it's called polar graph paper. You actually find it online and print it out for the cost of paper and ink. Or you can go buy a tablet of it. Pi over 6, of course, how far would I rotate? What's that? Yeah, 30 degrees, so not too far. And then I want to go out 6. So what polar graph paper does for me is it indicates how many, so 1, 2, 3, 4, 5, 6. So polar graph paper has all these multiple circles on it, and they represent the different radii. How far out do I want to go? So that's where I am. Now what I'm really trying to figure out then is what that x and what that y is that represents the same point in space. So what we have here is this triangle. So everything's nice here. We have this angle, and we have this r. We know what r is. We want to know what x is. And we want to know what y is. So the angle is pi over 6. The r is 6. How am I going to get x, for example? Yeah, cosine of pi over 6 would be what? X over 6, right? Just making the ratio x side over the hypotenuse. So x equals 6 cosine pi over 6. Should not be a surprise because x goes like cosine. So not surprisingly, y is going to be y equal to